to introduce you to Amber. And Amber has also a tremendous scholarly output, I would say, and everything that she has written kind of advances also our understanding of chemistry education or in the field. And she always pushes us to think further. And I guess you also have published a lot of things that kind of relate to Marcus, kind of to move beyond on what is possible. So Amber graduated from the Florida State University, if I'm correct, under the supervision of Jeff Areca. And she was a remote postdoc with Ginger Schultz at the Michigan State University. And she kind of said earlier when we started this meeting that she accepted a new job. So she will work at a company called Catalyst Education. And she will be working with faculty on lab instruction and hopefully making teaching a better endeavor. So congrats on that, Amber. And with this being said, you can try to share your screen and then you can go ahead.
Okay, are we seeing my presentation?
Yeah.
Yes, okay. Awesome. Thank you, Nicole, for the introduction, and thank you to Michael for inviting me to speak at this symposium. I'm really excited about it because, like Nicole said, I've been working on this kind of thing for a very long time. I started back in graduate school, I think in about 2017 is when I first started looking into this. So long before we were thinking about ChatGPT and everyone was talking about the large language models. So yeah, what I'm going to be talking about today is trustworthiness in machine learning. So sort of stemming from, I guess, what Marcus was talking about and the bias and how we can look at sort of more deeply what our machine learning models are doing when we're using them in education. I started doing this work when I was at University of Michigan with Dr. Field Watts mainly, and that's the book chapter that Michael linked for a publication for me. And then about a year ago, I started collaborating with Paul and Nicole to expand this a little bit. So the goal of this project was to go beyond accuracy when just looking at evaluating predictive machine learning models and to increase the trustworthiness of those models when we're using them in educational and research contexts. And there are several ways that we can do this, but the main thing I'm going to present today looks at how we can apply models in new contexts and see how they perform. So sort of the framework that I'm using for this is looking at the attributes of trustworthy machine learning from Varshney. And I like this framework because I think it aligns very well with the attributes of trustworthy qualitative research from Lincoln and Guba. If you do qualitative work in chemistry education, you're probably familiar with these attributes. And the four attributes that Varshney gives can sort of align each with an attribute from Lincoln and Guba. So the first is performance, which asks the question, does the model perform the task accurately? Whereas when we look at credibility for qual research, we're talking about, are our findings correct and accurate? So the theme there is accuracy. Secondly, reliability, which is a lot of what I'm going to focus on today. Ask the question, does the model perform consistently in real world context? So not just can it perform in the context that we trained it in? When we look at dependability in qual research, we ask, would the findings be consistent if we repeated this study? Then looking at human interaction, this asks the question, is the model explainable or interpretable to humans? Whereas confirmability asks, did the data support the researcher's interpretation? So that sort of focuses on interpretability. And then finally, aligned purpose, which asks, does the machine learning purpose match what society wants? Whereas in qual research, we have transferability, which is, are the results applicable in other contexts? So that centers around applicability. So mainly in a lot of publications, we see that we focus on the performance and we look at how accurately our models align with what humans would identify. And in this case, today, I'm going to focus more on reliability. So we can see the model is able to provide feedback for students in multiple contexts and not just in the context that it was trained. So the model that I'm looking at today, it's a model that is meant to provide formative feedback to students in an automated way. Some of you may have heard Field talk about or read his publication about how about using this model to provide feedback to students with an automated tool that would provide them with different features of mechanistic reasoning that are included in their writing. So we started with 2 writing to learn tasks. These are full-length written essays that students provide, about 500 to 800 words, where students, for part of it, are asked to describe what is happening and why in a mechanism. So we have our thalidomide assignment, which includes 2 mechanisms, the thalidomide hydrolysis, as well as the thalidomide racemization, and our Wittig task, which looks at a base-free version of the Wittig reaction. Both of those are published sort of in a qual way, so you can check those out if you want to. But what we did was we took 40 student responses to each of those prompts, which is a total of 120 mechanisms. And we analyzed at the sentence level for the different features of mechanistic reasoning that were included. So we ended up with over 1,200 total sentences. And our goal here was to look at features of mechanistic reasoning. So what we started with was a framework for mechanistic reasoning by Russ et al. And we adapted that framework based on the data that we had here. So these are sort of our features of mechanistic reasoning that we ended up with after that analysis. And they're in 4 quadrants, ranging from explicit to implicit features and going from static to dynamic features. One of the reasons it's really important to think about reliability and trustworthiness for this model is we adapted this framework specifically based on the data that we had. So taking it and applying it to a new context might be a little bit tricky because it was stemming from the data. So that's why it's important to look at how it performs elsewhere before we just blindly apply it to new context. So an example sentence about how we applied these different mechanistic reasoning features. So the student here says the oxygen has a positive charge. That would be labeled as charges. Oh, and I should mention these were quoted at the sentence level, but here I'm just highlighting the specific part of the sentence that caused us to apply the code. So the oxygen has a positive charge as it bonds with the hydrogen. This is an example of our dynamic code, bond breaking and making. And thus the water molecule will attack. So when a student says the water molecule will attack, that's an example of a non-electronic mechanism, meaning the students are not using electrons to talk about the mechanism, but they are talking about a mechanism. It will attack the double bonded carbon and oxygen group. That's one of our codes, connectivity. That's a static code and an explicit code because that's something that we can see explicitly on the page when we're looking at a representation. And then as it kicks off electrons from the double bond onto the oxygen, that's an example of electron movement. So the student is actually talking about the mechanism in terms of how the electrons are moving. And then we have an implicit properties code. So in this example, it says the carbonyl groups are highly polarized. The implicit properties are just any sort of properties that a student has to infer from the diagram that they were given. So things like polarizability and electronegativity, things that we don't usually see on our diagrams. And then that student says, because oxygen pulls on the electrons more strongly than the carbon pulls, and that's an example of our electronic causal reasoning because they're using the electronic implicit properties to explain an activity that's occurring. So that's just a quick overview of what students would be given in form of the feedback from this model. So to make a model like this, there's a process here that I'm going to walk through. First, when you're making a supervised machine learning model, you need to work on labeling the data. And in this case, we started with those 1,200 plus sentences, which Field and I labeled together. It's important to do inter-rater reliability here because you want, and this is sort of, I guess, part of the conversation before, you want to be reliable as a coder so that the machine can also be reliable. So in this case, we were about 69 to 79% in agreement. So what we decided to do was consensus coding. So anything we disagreed on, we discussed and came to a consensus before we used it to train the model. And how training the model works is you need to partition your data. You split into a training sets of validation and testing. So training and validation are used as part of the training, but the testing set is a holdout set that you set aside and don't use for the training so that you can test how your model would perform on data that it wasn't trained on. So then you use that data to train your machine learning model. And then finally, how we generally evaluate model performance is comparing how the computer performs to how the human labels things. So we can do this with more traditional IRR things that we use with human-human, which is like percent accuracy, Cohen's kappa. There are some other metrics that we use in machine learning more often, like Matthew correlation coefficient. And we can also look at things like a confusion matrix, which is what I'm showing here, where we can really see where we're going wrong with the model, I guess. We can see what mistakes the model is making and look more deeply there. So this is how we do it, but we have to choose what type of model to use. And there are two main types of categories of machine learning models that we use, and that's classical machine learning methods and deep learning methods. The classical machine learning methods are things like logistic regression, support vector machines, decision trees, and those are all things that have been around for a very long time. Deep learning methods are more new. It's things like neural networks and large language models. Large language models, for example, is GPT, what ChatGPT is using. There are pros and cons to each. So the classical models, they're easily interpretable by humans generally, or at least more interpretable than the deep learning models. For example, a logistic regression, you have your different features and their coefficients, and you can sort of see how like the inclusion of different features impacts the final decision. These are also less computationally intensive. These can usually be done just using a regular CPU. It's very quick, less environmental impact of training those models. But they might struggle with more complex language tasks. And that's where it's better to use a deep learning model. So those tend to have very high performance on more complex tasks. And you don't need as much labeled data because they use a pre-training, which I'll discuss in a minute. The cons of that, though, very computationally intensive, very expensive to train. Even for the part that includes our labeled data, it's more expensive because you need to use things like a GPU. It's more difficult to program. The classical machine learning models, a lot of times you can use one line of code to train those models, but it takes a lot more effort to train a deep learning model. So generally, we try to look at the classical machine learning models first and see if they work for our task. But if they don't work for our task, then we need to move on to deep learning models. And in this case, the classical machine learning models were not accurate, so we had to use a deep learning model. So what we used was BERT, and this was very state of the art a few years ago. It came out before ChatGPT. Basically, what it is, it's a model that was pre-trained on a very large corpus of text data, 32,000 million words, things like English Wikipedia and some other things. And so that pre-training is all done and you can download that model. And then you use your specific labeled data to fine tune it to do specific tasks, such as sentence generation or labeling, which is what we were doing here. So this is our original model that I did with Field. I have the results of that one here. This is already published in the book chapter. But basically, what this representation is showing is in the blue dots, we have percent accuracy, and in the red dots, we have kappa. And so for the different features of mechanistic reasoning here, I've shown the dots over on the right side. That red line is the cutoff for assessment. So generally we follow a rule that we want our model to perform above 70% and above a 0.7 kappa in order to use it for our formative assessment. And I want to emphasize that we are just using this for formative assessment, not to assign grades. It's to be used as a tool by students to help them with their independent learning or to evaluate sort of how they are doing when they're doing a writing. It's not to replace an instructor, it's to enhance the tools that we're providing to our students for learning. So you can see that all of the different features, we have kappas and percents above that 0.7. So we were really happy with how that performed. And to get there, we did have to continue adding additional sentences to help the model, because you can see that we had to add some additional sentences to help train like our non-electronic mechanism and our electronic causal connectivity of molecules, because the model was struggling with the data that we had given it. So we went and found sentences that we thought would be informative to the model about those different features, and we added those into our training set. So that was our original model. Looking at reliability. So this is where the collaboration with Paul and Nicole comes in. With reliability, we want to look, does the model perform consistently and accurately in real world context? So what we did with Paul and Nicole is we were able to add their data in to our model in order to test if the model would work in other contexts. So, and also Paul is doing his own thing. I don't think he's talking about it today, but he's doing his own thing with my data as well. So hopefully that will be a publication we have out soon that you can look at. But okay, so we looked at 2 additional sets of data with a different mechanism task. So the first set is the data from Paul and Nicole, and it's a different item type than we used before. Remember, those were long writing to learn assignments. It's from a different university. Here we used an entire response because they're short answers. They're we're not looking at them at the sentence level. We can look at an entire response because the word count is not 800 words. It's closer to 100 words. And for that one, we ended up with 818 total responses from 2 different tasks. And then a second set is from another assignment. We pulled it from another assignment that we had, which was asking students to provide a statement about if reaction A or reaction B occurs faster in a case comparison. And so again, this is a third different item type. It is from the same university as before, but it's the entire response, not at the sentence level. And we have 3 different tasks for that are across different points in the semester. So we are changing up the level that the students are at when they're responding. And for that, we had 1,200 responses from 3 different tasks. So what we did, we took BERT base uncased and this is just for anyone who is interested in the more specifics of the model. It doesn't really matter that much to those of you that don't understand BERT models, doesn't matter, but we use BERT base uncased. We tested 2 different learning rates. We tested a range of number of epochs from 1 to 100, and then several different batch sizes as well. We did find that the lower batch sizes tended to be better, and that takes a lot more training time, which makes sense that it would be better with more training time. But yeah, generally the lower batch sizes, 2 or 4, are better. So what we did was we had several different things that we tested, but the ones I'm going to focus on here. First, we took our original model and did external validation of it with both new data sets separately. We also worked on adding that new data to our training set and then testing the new model with different holdout testing sets from those 2 new sets. And then we also took all of the mechanisms that we included and we balanced the model training. So we took an equal number of training data from each of those different mechanisms and only put that in the model. So that's a little bit less training data, but it's balanced across the different mechanism tasks. So what sort of results did we get? Well, this is a similar visualization as before, but the blue is now from the original model and the kappa from the original model, and the red is from the new model. So this is our data set number 1 that we're adding in. So looking at our very original model that we had and all the different features of mechanistic reasoning, when we just applied it without adding anything else into the training set, it didn't perform that well. You can see that only a few of them made the cutoff that we want to make for formative assessment. But when we added in that to the training data, and then we had a holdout testing set, almost all of the features of mechanistic reasoning the model could then do, which would make sense. We added in that data and now it can learn about it. So there's a couple things to say about that. One being that it couldn't transfer to a totally new context with different different tasks, different mechanisms very well. But when we were able to add it, the model did adapt to be able to include those things. So it's positive because we can adapt it that way, but it's also cautionary because it means we can't just blindly take it and transfer it to a brand new context. The reason that the formation of stereochemistry one is so low is because this data set had essentially no formation of stereochemistry in it just because of the nature of the questions. So because the model didn't get any information about that, the model couldn't learn how to do it. So moving on to our data set number 2, we see some similarities here. This data set didn't include any of our reaction medium code at all. But with the blue, we can see it doesn't perform well at all before we add in our data from this set. So again, looking at another new set, another new question, the model can't transfer to it without adding in training data about it. So it's very important for us to take that into consideration. If we're taking a model and trying to put it in a new context, we need to be sure that it will perform in that context. So looking at our original model, so our original codes with our original model, that's what we see here in the blue. And when we added in the additional data from the 2 new data sets, you can see it stayed pretty much the same, indicating that what we did previously with adding in extra data for the codes that were tricky, we pretty much had reached saturation there for how well we were going to get this BERT model to perform. So they're pretty similar when we add in the new data because it's not adding any new context to the model for this set because it's not more of this data set for training, it's new set. And then with the balanced model, it's pretty interesting for this one because it's all over the place. A lot of it performs worse for this model. And I think that's because, like I said earlier, we had to add in a lot of extra sentences for some of our codes. And when we take away training data, the model, this was too complex of a task for the model to still understand how to label things. So while it's good to have a balanced set, for this case, it didn't work out. You'll see more in the paper that Paul and I are writing about how this worked for some of the other sets, but in this case, it made it quite a bit worse. Okay, so just a little bit about the human interaction aspect of trustworthiness in machine learning. So looking at if the model is explainable or interpretable to humans. Like I said before, the deep learning models are kind of difficult to interpret. And so in order to explain how that model works, we need to use additional tools beyond what we use to train the model. So an example of this where you can that you can use to explain BERT models, there's a lot of other things you can do, but one option is SHAP, which is short for Shapley additive explanations. It's a concept from the math world, but there's 2 ways you can look at how the model works, and that's locally, which is looking at just how it labels a single response, and globally, which is looking at how it labels the set as a whole. So locally, when we look at individual labels, that's generally edge cases, things like where the model did not accurately identify what it was supposed to. So false positives, it thought it was there, but it wasn't. False negatives, it didn't think it was there, but it was. And then when we look globally, it's what features of the writing in general contribute to how the model makes decisions for that label. And what we're looking at here is sort of qualitative. If the features used to make the predictions make sense compared to how you as a human would label a response. So I just have one example of this here locally. This was for the electronic causal code. Different models range from kappa values of 0.65 to 0.75 for this, but this is a false negative example. So this student said, for this reason, it is more stable for there to be a racemic mixture. And the model thought that this was the model thought that this wasn't a electronic causal, but we thought that it was as humans. So we can look at how these different features contribute to it. So we do have a lot of things contributing a lot of words there that can contribute to it, but we don't have anything really contributing in the negative direction. We only have our period here. So there's not enough information for the model to label this, basically, is what we're finding out. So it's important to sort of look at those cases and see where we might need to add in more data to our training set that can contribute to it labeling something like this, basically. So in sort of summary, we looked at accuracy, reliability, and human interaction. I haven't looked, or I don't have all of the data, I guess, to look at the global explanations. And I wanted to just be quick to show you what SHAP could do. I have many more examples at the local scale, at the local level there. But I wanted to show sort of how we can look into the model's decision making. In conclusion, the model performed poorly in most categories when we added it to a brand new context. When we were looking at reliability, it was not reliable before we added in additional training data. But it did perform well in most categories after we added in the training data. So that's positive because it can be transferred. We just need to add that additional data in order for it to work. So it's very important to consider new context before we just take a model and implement it in our classroom without looking at that. And we need to do more work in order to show further the interpretability of the BERT models, because I don't have that data yet. But like I said, I am working on it. So that's something that you will see in the future in the publication. So that is mostly it. I wanted to acknowledge some people that worked on this with me, Dr. Solaire Fingerstack-Quinn, the Schultz group, Professor Ann Gear, who really piloted our MRIGHT program, which is where all this data came from, as well as my co-authors. Field did a ton of work on this, and Paul is currently doing a ton of work on this. So I really want to thank them. And if you need to contact me, that's my new email address that you can contact me at. So I can take any questions.
Thank you very much, Amber. I guess you have a perfect example how important it is kind of to work together and to collaborate